just...
Obrigado, Conrado. Can you share the full screen?
Now what do you see?
Still presenter mode, I think. You see okay?
Yeah. But this is the presenter mode, no? I don't know why it's not...
But you need to first open the presentation and then share.
Yeah, this is the presentation.
So you first
Because I'm sharing the whole screen. And then...
but you're sharing this screen, not the other one.
Yeah, so what should I do here? To click on present? Well, maybe stop and...
Stop screen. And start again, and maybe you can choose a live screen. Present. Yeah.
For me, sharing the whole screen was...
Screen share. Yeah.
What we did before, allow share screen. And then when I go here, I don't know. Okay, so here I share the entire screen. Unless I share
Can you go back to the...
and then here slideshow.
Yeah.
But I don't know what. Because I think he recognized the... not sharing it?
Which...
This thing.
Oh, there's some delays. There's some delays. There's some delays.
And the group here is not present.
Oh, wait, I have to press here. Wait. Wait. Yeah, now it's not sharing it.
I can stop.
Okay. Can you try to share now?
Yeah, I am sharing to edit, but
Yes, now you're sharing your entire screen.
okay. Now if I go here,
Yeah, I think that's the...
fortunately I think what happens is that
It's sharing your
Use
screen.
slideshow.
okay, perhaps yes, you're right. Yeah, very good. Okay.
Oh, Conrado solved the problem. Very good,
Yes.
Conrado. Mathematician. Mathematician always solves the problem. Okay, so let me just introduce you in 2 minutes.
Yes.
This is the camera. Let's see how we doing with the camera. You're gonna be more over there, right? Step back a little bit.
Step back.
Yeah. So, good.
My best profile is the other one. I can present like this. Yeah, good.
Okay, sorry everybody for the delay in getting things set up, but now we are set up. We are broadcasting live. Giovanni's talk. It's also going to be recorded on YouTube. Let me do just a quick introduction. Giovanni Neglia. Well, by the way, I am Daniel Figueiredo, professor here at PESC and collaborator of Giovanni. And Giovanni is visiting us for the week. He got his PhD some time ago. And we met when we were both PhD students many years ago. And he has done his career at INRIA in Sophia, Antipolis, in France. He started working in performance evaluation of computer networks. That's also my original area. And then he moved on into network science, working at models for networks. And more recently, he was sucked in by the black hole of machine learning and jumped into learning and has been working the last years with federated learning, which is a topic of his talk today. So Giovanni and I go back a long time, as I mentioned, and we had a joint collaboration project funded both by FAPESC and INRIA, which lasts, I guess, 5 years? 6 years. It was a very productive time, and that was already 10 years ago. So he's coming back to Rio after 10 years, and we hope to get something rolling. And it's always a pleasure to have you here, to see that you moved on to this next step in your career. it's nice to see that you have this flexibility to adapt and learn and do great work. It's something that is common to Giovanni's work. If you look at his papers, they're always very good. And we are motivated. There's always a nice contribution. And it's good to see that you can do that, evolving and learning over time. So it's always nice to have you here. Thanks for coming. Thanks for visiting us again, and look forward to your talk.
So good morning, everyone. I want also to thank Daniel and the other Daniel Sadocchi for hosting me. It's always very nice to be back to Rio. I think it's my 4th or 5th time here. So today I'm going to talk about federated learning, and it's it's going to be a long talk, and it's 45 minutes. And so if something is not clear and you feel like that this may block the follow-up, don't hesitate to ask directly, okay? I think then it's up to me to say, okay, this perhaps we will clarify later. Okay, so where I come from, so as Daniel mentioned, I am from INRIA, so it's the French Research Institute for Computer Science. And there are different centers all over France, and I am from a nice one. I think it's the nicest one, geographically speaking. Not as nice as Rio, perhaps, but we are here in a technological park whose name is Sophia Antipolis, and is midway between Nice and Cannes, and we have this nice cape in the middle. Okay, so what I've been doing in the recent years indeed is about distributed machine learning, both for training and inference. We are always looking for smart and hard-working people, and so in case you are interested to go to Europe, or there are a bunch of positions you can look at, or just come to talk with me. So let me introduce you federated learning. So you know that machine learning is about data, and this data usually is generated by the user. You generate continuously data with the picture you take, with the text you write, and so on. So the usual classical step is that you take all this data and you collect in a single point, and there are then, let's say in the cloud, and there you train a model, maybe a big model, let's say a state-of-the-art model for inference. I think
It's not working.
yeah, perhaps it's the battery, perhaps. So it can be a big model for inference from the cloud, no? Or can be a small model that later you ship to the devices for inference from the device. So like 9 years ago, Google thought, what if finally we are going to train a model that is going to be used to the smartphone, why don't we directly train on the smartphone? Okay? And the main motivation they put forward was that collecting all this data at the same location may be expensive. This was appearing in the first paper. Since then, the kind of story has a bit changed, and today they put forward the fact that they want to protect the privacy of your data. So if the data stays at your mobile, then it's okay, you should let us train the model because we don't learn anything more than we should learn about it. And moreover, recently there's been also some people that have been arguing that perhaps these decentralized distributed solutions may be also more interesting from an energy point of view. It's debatable. Okay, so what happens then is that there's a central node that coordinates the training, sends a tentative model to all the devices. The devices update this model on the basis of their data, and they send it back. Then this model is aggregated, and everything is repeated multiple times. Okay, so this is a relatively simple scenario, no? But you can imagine that there are a lot of problems because these communications are slow, are not reliable, people can just disappear, and moreover, the local data set can be very different, both in terms of volume, in terms of quality of the data. But in general, you should see that this data comes from very different distributions, no? if you check the pictures that I have in my mobile are maybe very different from the picture that you have in your mobile, because geographically we live in different places, because we have different interests and so on. And this affects the training. So this setting is what is called the cross-device federated learning setting. And nowadays all the big actors in like Google, Apple, Facebook, etc., they all use Amazon, they all use federated learning to train some model. The most, no, the first one probably was a Google Keyboard next word prediction model that has been trained with federated learning. But the world of federated learning is not limited to these big actors, but there are a number of stakeholders that are also interested in this solution. For example, you may imagine hospitals that want to carry on a medical study, you know, of some disease, and they cannot really share the data of their patients because, you know, this is not something simple to do. And so they may use federated learning. Okay? Or you may have a company that has headquarters in different countries, and I recently discovered that in Brazil you have quite strict rules, as we have in Europe, about the fact that the data of Brazilian people cannot go out of the country. So in this case, the company may be forced to use federated learning if it wants to train a model using data from people coming from different countries. So the idea is a bit the same. You can imagine that here you have, you have much more computing resources, you know, reliable connection. So there are some stuff are similar, others are different. And tomorrow you can imagine that things may be even messier. But, okay. So federated learning is a very active research area. So there are a number of papers every year that appear related to how to make federated learning an efficient way. What about the privacy of federated learning? What about the robustness to attack? It's a distributed system, so you can imagine that you know, it's easier to attack. What about the model that we finally learn? Does it work? Is it good for everyone that has been participating, or you know, the model may be a bit unfair? And finally, what if we try to participate to this learning, but finally get a model that is more suited for our specificity, so like personalized federated learning. I have been working on almost all the 5 of this research area, but I've been so for this today we've been asked to focus on 2 aspects. So the first one is everything that is related to, you know, aspects related to communication problem, networking problem in federated learning, and the privacy aspects. So I will try to do my best to cover these 2 points. And the first thing perhaps that is interesting is it really a difficult problem, no? Because I presented this kind of distributed approach, but for those of you, I mean, perhaps you don't need even to be expert to know that when we train a model, usually we use already multiple GPU across different servers. So what is different here from what's happening in a cluster, okay? And just for, in case there is someone that is, you know, doesn't come, you know, hasn't been exposed to machine learning yet, a couple of slides. So what the goal is to learn a function that maps some input to some output, and we want to learn by using a data set. Okay? So the simplest things you may imagine is that you want to learn, for example, a linear model, so you're doing linear regression, for example. And so the way you do is that you minimize an empirical loss. So you have a function that tells you how good is your model on a given input, and you sum this loss over all the points. And you may have an additional regularization term. Okay. Okay, so in order to illustrate why perhaps we could be surprised that we are doing a big fuss about federated learning, so we need to consider how do you really learn in practice, and for different reasons we use very simple algorithm. I mean, we have tens of years, hundreds of years on optimization, and finally, what we are currently doing are variant of gradient descent. So you start from a tentative model, you look in which direction the loss is increasing, and you move in the opposite direction. So it's a very simple algorithm. And now let's try to implement this algorithm in a cluster. So what the issue is that you could theoretically do with a single GPU, but if you have a big data set and you want to load and offload the data from your GPU, this is going to take a lot of time. So what people have been doing is you take the data set, you split, you distribute it to different GPU, and then all these GPU work in parallel. And so what you can do is then you slightly redefine your problem. So you can think that you define some local losses that are now the average loss on the data that every machine has. Okay? And you rewrite your problem as minimizing an average of losses. Okay? This is just trivial math. And now what you can imagine is that you apply your gradient method, and because the gradient is linear, what you have exactly the basic gradient method you can rewrite as updating your model with an average of the gradient computed on every loss. Perhaps I made too many words for something very simple, but so this gives immediately a parallel way to implement a distributed gradient. That is what happens in a cluster. So what happens in a cluster is that you split the data, and then you have a node that coordinates the operation. It's called the parameter server, usually in the cluster setting. This parameter server sends the current model to every worker. Every worker computes the gradient on its own data, send back the gradient to the parameter server. The parameter server average, and then updates the model and sends the model back. Okay, so this is what happens, let's say, model a lot of details, but what happens in the cluster. And we've been doing like this since at least 20 years. So why we gave a different name to what's happening on the internet, why there is a full branch of people, a bunch of people that work on it, isn't the same. And the reason why we're talking about it is because indeed we wanted to talk about a networking challenge. And here everything is about the network, everything is about the communication. Because now we can put, we can check, okay, what happens if we do the same at the scale of the internet. And here you have some numerical example. You have a smartphone, so it takes longer time to compute even a smaller batch. So this is an outdated model, but was taking half a second to compute a gradient. But what happens is that if you look at the time you spend to communicate, this time is order of magnitude larger, okay, than the reputation time. So for example, if you want to transmit a 10 megabyte model over 1 megabit per second link, well, this is going to take 80 seconds. So if you take the same algorithm and you implement at the scale of the internet, it's going to take forever. And you essentially compute, one time, and then you wait like 2 order of magnitude larger for something new to happen. Okay, so that means that we cannot really do exactly what we were doing in the class. So what is the idea? Well, the idea that this smart Google engineer had was quite naive. Is okay, if communication is a problem, why don't we communicate less and compute more? But they are well paid to go through these things. So what happens is that then you send the model to the device, and the device, instead to just compute one gradient, performs locally multiple steps of gradient descent, and then after a capital E step, sends back the new model. And now when you have all these models. The orchestrator, what it does, it averages these models, and everything is repeated. Okay, so that's the first algorithm that was proposed for federated learning. Is called federated averaging, and it's still a kind of like the baseline. So it still appears in the paper. It's a relatively good algorithm. And so sometimes it's nice to go back to the older paper. So this is the first paper that is there, and there is this sentence that is nice. It is impressive that averaging provides any advantage. So they were not expecting that this was working. Okay, this may seem naive, but you see, everyone is optimizing a different function. You get a new model, you send back and you average. Why this should work? No. In fact, they were, they found it surprising. And okay, we can discuss. But another index that was not so obvious that this was working is that it took around 3 years before we had the first proof of convergence of this method. Okay? And this is what the kind of convergence they look like. So let's take, for example, one result. This is classic assumption that we do optimization, smooth convex, smooth function, strongly convex, etc., etc. So you see, this is how far you are from the optimum. The good news is that it decreases with a capital T, that is the total number of gradients computed by a client. But you have some term that depends on the heterogeneity of the functions, and it depends on how many steps you do locally. And this is for the time, sorry, this is not the time, this is number of gradients. Now, if you look in terms of time, what we should do is that if we assume that the time is essentially spent communicating, if we take the number of gradients and we divide by the number of gradients that we do in every round, we get a rough estimation of the time. And now when we do this operation, what we see is that the time, so the number of local steps has a double effect on the time. There is an increasing term in E and a decreasing term in capital E. And so this is what you observe from the math. So that if you communicate, if you do a bit more local steps before communicating, it helps the training time, but you shouldn't exaggerate, because otherwise it works super bad. And this course, well, this math is interesting because it kind of matches what the people were seeing in the first paper, that there is an optimal value that is some way in the middle. Okay, so that is, like, there has been this, so this algorithm, new family of algorithm was motivated by networking problem, and that were serious, so we couldn't, it would take perhaps years to train a model without coming with new algorithm. But is it at the end of the story about networking problems in federated learning? And not really. There are many problems that you may think about. So, for example, if your name is Google, when you train a model, you have potentially hundreds of millions of people that can help you. It's a good news, but at the same time, you send 10 megabytes to 100 million people and you wait for their answer, you are going to be flooded from the answers. So it's the problem of the volume of the data, and there is also a problem of the stragglers. So you know that even if you are in a nice cluster, all the machines are supposed to be the same. You tell them to do the same task, they should come back to you exactly in the same moment, but there is a lot of variability for plenty of reasons, from garbage collector to other stuff. And here the system is more wide. I mean, the machines are not definitely the same, and they do a bunch of other stuff in parallel, so there is a lot of variability in the time they send it back. So what are solutions to this problem? So these are things that, as master, as a student in computer science, you may think about. So perhaps what instead to have this asynchronous system where you wait for everyone before updating the model, you could imagine that you as soon as you get some new update, you integrate in the model and you update the model, you set back. So some synchronous operation. People have been working on it. The problem is then to prove that these asynchronous algorithms still converge. To reduce the volume, you can, instead to aggregate at a single point, you can progressively aggregate in the network. There is work on it. If the problem is the volume, you can compress. Instead to use 4 bytes for the values, you can go down to 8 bits. You can, instead to transmit all the components of the model, you can just transmit the biggest values. Perhaps they are the most important. All of this has been considered in the literature. Obviously, you sample I say that you Google contacts all the hundreds of millions of Android devices, so this is false. You sample people at every round. And finally, in terms of communication problems, you can probably get rid of this star system, this master-slave architecture and go decentralized. And this is what I have been concretely working on, so I will talk more about it. Okay, so here we have a star topology with all these problems we have discussed about. So what if we go really distributed, or if you want what is called sometimes decentralized federated learning or peer-to-peer federated learning. So here you have the clients. They now are organized in a topology, in a graph, and they receive update from their neighbor, and they send update to their neighbor. The graph may be oriented or not, of both possibilities are there. So there is a whole family of algorithms that actually was originally is a contribution of the control theory community. People like Dimitri Bertsegas, Tsitsiklis, Osdaglar, Negic, etc. that have been looking at this consensus-based distributed training, you can call it. It was not for training. They were not at that time. They were not. There was not the buzzword of machine learning. They were just talking about distributed optimization. So the way this algorithm works is the following: every client gets a model, let's say, from its neighbor, and then average them with some weights, Pij. And then in plus, moreover, it updates the model with some local gradients, and this is repeated over time. Okay, now, so there are convergence results for this algorithm, etc., etc. But as a person that comes from the networking world and also worked for a while on network science, I obviously was curious about how should we design the topology, And the main metric you would like to minimize is the training time, So what you would like is to design topology that guarantees you that the model is trained in the shortest time. And now, how long is it going to take to train a model? Well, it's going to depend on the number of rounds and the duration of a round, okay? And what is the effect of the topology on these two quantities? And as you can imagine, the effect is kind of different, very different, and sometimes really opposite. So, for example, if you have a less connected topology, you may think that every round will take less.
What is a round?
So a round is one iteration of the algorithm. So you get the model from your neighbors, you update doing one or multiple step of local gradient, and then you send. And this is a round. Okay, so if the topology is less connected, you may think that this route will take less. Why they will take less? For example, because you wait for less people. So the struggle problem will be less heavy. Also, if you need to pick less neighbor, you can select them more in a better way. So perhaps you can just talk with the people with whom you have a very good connection, high speed connection, low delay, etc. And then finally, if there are less connection, probably there are less message going around, so there is less network congestion. Okay, so motivations to select a to select a connection with a few, so a topology with a few links. But at the same time, as you can imagine, if there are less links, the graph overall is less connected, the information doesn't flow very well, and this means that we may need more round to converge. So there is two different effects that on the training time. Okay, I have been working on it, I have a bunch of papers, but so let me present two of them. So in the first paper, or in this paper, we were considering how we should select the topology in order to have the fastest possible round. Okay? So we are just looking at this problem. And so this actually happens to be a problem in which there was a lot of math already done. And so there are exact results that tell you asymptotically over multiple iterations how long is a round going to take, okay? And so let's look at what these results tell you. So essentially they tell you that there is a topology. So you take a topology, you consider a cycle in the topology, and then there is a time associated to do the tour of the cycle. No? Think the delay on the links, the computation time in the node, etc. So you take this time and you divide by the number of edges that you have in the cycle, and it's a kind of like average per link delay of this cycle. Then what you do is that you look at the worst possible cycle. So the cycle on which this number is the largest. What you get is the asymptotic duration of a round. So you see, if you let this system run, and then you look at all the rounds that are finished over time, well, this converges to 1 over this quantity. So now we have this math that was not our math, we just recognized that we could have used this kind of result. Now the question is, how do we design a topology that minimize this quantity? No? Now we have the good problem. Okay. As you can imagine, unfortunately, this problem is NP-hard in most of the cases, but there are a few, well, there is essentially one case where it can be solved exactly, it's polynomial. That is the case where the graph is undirected and where you only have delay on the links. So if essentially the delay comes mostly from the communication part and the graph is undirected, then you can solve exactly. And the best possible topology is a minimum span interval. Okay? In the other cases where the problem is NP-hard, well, we had the approximation algorithm that produce also kind of very, very economic topologies like rings or some other form of trees. Okay, so we have this result, and then we evaluated on some realistic topology, actually some real topology more than realistic topologies. And what we saw is that indeed there were quite some saving that you could achieve in terms of reducing the round time with our algorithm, and that this saving were propagated to the training time. Okay? So this is not obvious because, as I told you, yes, now we have the fastest possible topology, but perhaps we will need more round to arrive to the convergence. But okay, so the result shows that you had, from okay, I think this is what Google is doing, let's say, and we could get a speed up of up to a factor 10. And this was the competitors with whom we could get a speed up to 6. Okay, so good news. And by the way, this result shows that sparser topology are good, and here we are not considering the effect of congestion. Here there is no network congestion. So if you take into account the fact that there may be network congestion, then our algorithm will be even better because they really communicate the minimum possible. Okay, now I would like to talk about the other aspect. So we said the topology, sparse topology are good to reduce the duration of time, but what about the number of rounds? And we have this intuition now that if a sparser topology probably leads to the information to travel slower in the graph. This actually can be made formal. If you look at the paper from the control theory community, you have this kind of result where so you have a convergence, but this convergence is affected by the spectral gap of the matrix P. What is the matrix P? P is the matrix that is made by all the weights that you use in the consensus path. And the spectral gap is, let's say, the difference between the largest eigenvalue and the second largest eigenvalue module. So it's known to be an index of connectivity of the graph. So if you have a very well, the clique has this number equal to 1, and if you have a poorly connected graph, this can be arbitrarily close to 0. So this can blow up. And the other element here is the alpha, that is the learning rate. Now, usually the way people present this bound is they tell you, look, the learning rate has 2 different effects. So in some sense, for this term, you would like to take a big learning rate. For this term, you would like to take a small learning rate. You do the derivative and you pick the learning rate that minimizes the whole bound. If you do this, you should take the learning rate, a learning rate that grows as square root of the spectral gap. You plug in and you get this kind of bound as a result. And this is the way usually it's presented. And the people say, look, poorly connected networks are bad because you will need a lot of RAM. Okay? And we were working on these things. We did our kind of experiment. You take the learning rate, the square root of the spectral gap, and you see what you expect. No? So you see that, for example, if you start from the ring takes a lot of iterations to converge, and and the more connection you have to the graph, the better it goes. And then one day you ask, and then one day the student comes and presents you this picture, where he forgot to tune the learning rate proportional to the spectral gap, and it shows you this, where all the curves overlap, no? And then obviously, you have done your job to read the papers, you repeat everything that everyone is repeating, so you tell to the student there is a bug in your code, go back and check. And the student comes, at the same time the student comes, you start saying, no, perhaps, it's not a bad student, perhaps he is right. And the question is, where this comes from? I mean, nobody said that there was no effect of the topology. And okay, this is I think sometimes these are the funniest part in the talk. That once you start having something in your mind, these things start popping up everywhere. So you go back to papers that you already read, and suddenly in the appendices you find figures that you didn't pay any attention to. So you start seeing that so there are a bunch of NIPS, SML paper, and so on that have this curve where they consider extreme topology like rings and fully connected, and the training curve almost overlap. And so you say, so there is something behind this, it's not only us. And obviously in this paper, nobody say a word about the topology, this is strange or whatever. Okay, okay. Now we don't go into the math, but so this is the real form of the bound that was existing in the literature, and that's suggesting heavy dependence on the topology. What we did is that we essentially derived a Teiber bound. And in this bound, the term that depends on the graph is multiplied by constants that are much smaller. So let me tell you a few things that make this constant smaller. The first one is that, you see, when people have studied first, and this E, it is kind of like the maximum module of the gradient, in some sense, that you can observe in the network. And what we realized is that in reality, it's not really the gradient that matters, but is how much the gradients of the different nodes are different from each other. So if, for example, all the nodes are computing exactly the same gradient, so they update the model in the same way, the topology doesn't matter at all. That seems trivial now if you think about it, because obviously everyone has the same model, the average models are the same, well, the topology should matter. But nobody had thought about it. And the second aspect is here, is that the boundary is a worst case bound, but in some sense consider that the gradient is aligned with the eigenvector relative to the second eigenvalue. That there is really no reason why it should happen. No? You have the gradient that depends on your data, and then you have a property of the graph, why ever they should be aligned. No? You can think that perhaps in general, in high dimension, they would be orthogonal more than aligned. And so all of these things contribute to make the effect of the topology much less important than what was expected. And okay, what is interesting then, that is always a satisfaction for a researcher, is that other people have been extending our analysis, and they've shown that it's not even the heterogeneity over the whole network that matters, but it's the heterogeneity in your neighborhood. So if in your neighborhood you see a data distribution that kind of match the average data distribution, then the topology doesn't matter. So that's that's what we did. And now, as you can imagine, at the moment we had some contribution on the effect of the topology on the communication round, some contribution on the effect of the topology on the number of communication round. I think I repeated some stuff on the duration of the round and on the number of communication rounds, and we should put it together, no? And we haven't done yet, so we are looking for a PhD student on this topic. Okay, now as we spend the no, I don't know how much.
Okay. See. Okay, 15 minutes.
Okay. 10 minutes. Okay. So as I told you, federated learning is for people working in federated learning. It's nice that Google and Apple and everyone tells you, we don't. It's very important. We want to do it, but honestly, we are a bit worried that this is a bit just of advertisement. Because federated learning allows them to say, we care about your data. So is federated learning really private? And fortunately, not so much. Not as you would think. So people have shown that even if the data stays at the client, if you look at this message exchange, there is a lot that you can infer. And in particular, there are three main attacks that people have been looking at. One is what is called the membership inference attack. You want to know if a given data point is in the data set of a client. And this itself can be important. No? Imagine that there is a medical study of hospital about a disease, and if you discover that a given person is in the local data set of an hospital, this is saying something about the person. So this is a membership inference attack. Then there are cases where there is a person, and you know a lot about this person. You know the name, you know the age, you know where it lives, but in the record there are some attributes that you don't know, and so you want just to reconstruct this attribute. For example, the salary, use of drugs, disease, etc. And finally, there are attacks where you want to really reconstruct the whole. You don't have any information. You want to just reconstruct the point. Okay. And here you see a few examples from existing paper where they show that you can essentially reconstruct image in the data set or you can reconstruct the text that was used, that is in the data. So I will briefly discuss through our contribution on attribute inference attack and on data reconstruction. So the first attack is there is a record of which you have a lot of information available. This is XP, and there is perhaps one attribute that you don't know and you want to reconstruct. What you can do, so there are two families of methods, gradient-based and model-based. So let me present to you briefly. So in the gradient-based, what you do is the following. You look at the update that the client has been doing, and then you compute the gradient of the client for different possible values, let's say, for different guess of the sensitive attribute, and you try to see which case much better. The way I presented you is a combinatorial problem. I have to try all the possible values. In reality, there are ways to map this to a continuous problem where you can do continuous optimization and it's much more effective. Do they work well? So let's look at the pink curve on top. Shows the success of reconstructing a binary feature as a function of the client dataset size. So you see if the dataset, the client has only 64 points, you reconstruct more than 3/4 of the sensitive feature correctly. And as you can expect, the bigger the dataset size, the worse the performance are. Because you see this aggregate update that depends on a lot of points, so it becomes more difficult. But it's still okay. But the results, people in the literature had focused on a classification problem. So we try to look what about the regression problem. And the story is quite different. First, we see that in general the values are much smaller. But moreover, starting from 256 points at the client, you are around 50%. That means that you are just randomly guessing. This is a binary feature. So even if I drop a coin, I get a 50% success. Okay, so that's the gradient method with. Now, there is another family of methods that is model-based. And here what we do, you have the model. You look for the value of the sensitive feature that minimizes the loss. Okay? And as you can imagine, this should work well if the model is is working the better, the more the model is overfitting the local data. So what we get in a federated learning setting? If we just apply cities, so there is a model that has been trained, we attack this model, we move from the blue curve to the red curve. It's better, but it's not, you don't write a paper on it. But at the same time, there is a lot of space for improvement. That is the green. What is the green? Is what if I would attack not the global model that we have altogether been training, but the model that would have been trained just from the dataset of this client. Now you see that the attack becomes close to 100% accuracy, and even if you go to relatively large dataset size, you are still above 90%. Okay, so what we would like is to, in a federated learning setting, to be able to lead the client to tell us what model it would have trained on its own dataset alone. Okay, that is our goal. So we try to get this model, that is the model that minimizes the local loss of the client, and then we attack with model-based attack this model. So, okay, so we have some results about linear regression that proving that you can just by looking without doing anything particular, you can reconstruct the local model. But okay, linear regression is not particularly interesting. So what you can do in general? Well, what you could imagine is the following: that the client has sent this model Well, instead to aggregate, you send back to the client the same model. So now the client starts from this model and computes additional gradient steps. And you repeat this. Okay? So this is just a way in which a malicious server can let the client compute for it its best local model and then attack this model. Is it slow? First, it is slow. And second, you understand that this attack is very detectable. No, because I send you a model and you send me back the same model. I mean, it seems strange, no? So now what you can do is you can add the momentum at the server. This speeds up the attack, and moreover, I don't see the same model coming back. So I may be trusted. And this works well, works quite well. Okay? So like, let's not go through all the figures, but essentially we are the brown over there, and the brown, so we kind of achieve the optimal performance. Okay, so that's an attack in, and we are much more robust, you see, to the size of the data set. We can go up to 30,000 and we still have a non-negligible accuracy of that. Okay, final things I want to discuss is what if I want to reconstruct the whole points. And again, there are two families of attacks. The first one is very similar to the gradient-based attacks. And so you have, the client has taken an image or a bunch of images, has computed an update of the model, and you know this update of the model. And now what you do, you look at the same box from another point of view. You start with a noisy image, and then you compute a derivative not over the model, but over the input, trying to modify progressively the input in such a way that the corresponding gradient maps what you have seen. These are the optimization-based approach that were kind of state-of-the-art. And by the way, these are the nice picture I showed you at the beginning. The nice picture I showed at the beginning are, but those pictures are for very small batches. Okay? So if you have a batch size of 4, 8, these are the kind of numbers that you see in these papers. So you are able to reconstruct the image, but just if the update has been computed on a small set of images. Already when you move to 256 images, this is the kind of things that you reconstruct. And we kind of see that there are fishes, no? I hope. I mean, at least I see fishes, but they are very blurred, no? These are not perhaps what you would like to obtain. Okay, so that's the optimization phase. And then other people have proposed analytical attacks. So imagine that you have your input that goes through some linear layer and then goes to a ReLU layer. Okay? And now you can have fun to compute what is the derivative of the loss with respect to the parameters of a given neuron here, neuron I. And you can also compute the derivative with respect to the bias of this neuron. And it's a funny exercise, I mean just a bit chain rule. But what finally you get is the following, that the derivative of the loss on point J with respect, the gradient, with respect to the parameters of the neuron is proportional to the input. So if this coefficient of proportionality is different from 0, you can reconstruct the input simply by division. So you have the gradient, and just by dividing a piece of the vector by a constant that is again a partial derivative, you can get the input. Okay? And you just need this to be different from 0. That means that you need to give as input to the ReLU a positive value. Okay? That's the attack. So, but this is when you only have one image. If you have a bunch of images, well, what you get are linear combinations of these images. Okay? And now, let's see what people had done before. What people had done before was the following, but they were not presenting with this schema. So imagine that you have your images here. You can essentially reconstruct in a very easy way every time you have only one image that is activating the neuron, and this will correspond to what? This corresponds to the fact that when you take the value of wi and b, you are identifying an hyperplane, and this image is the only image that is in the hyperplane that you are identifying. Okay? So this geometric interpretation was not really there. And so what other people were doing is the following. Okay, we know that it's very easy to reconstruct an image when it's alone. So they were kind of like throwing at random planes, hoping to isolate some point. Okay, so here you throw the blue hyperplane and you are lucky because you can decode this image. You throw at random this blue hyperplane and you can reconstruct this image, and so on. And you see immediately the limit that you can only reconstruct the convex hull, I mean the frontier of the convex hull, but you cannot reconstruct what is inside, you know? And then you can have fun to show that, yeah, I don't know if this is very interesting, but no, you can show that essentially the convex hull is almost always a vanishing fraction, or you know, you really need to put your points in a very specific way to have that the convex hull is a non-vanishing fraction of all your data. Okay. Okay. So what we did is simply say, but can we only really reconstruct the image when they are alone in the hyperplane? And not. So what we can do is to work with shifting the hyperplane and see what happens. So now when we do this, we have linear, what we observe no more the clean case where we just have something that is proportional to the image, but we have a linear combination of the image. And in particular, if we move the hyperplane and we observe something different, we know that in this slice there is a new image. Instead, if we move the hyperplane and the result doesn't change, then here there is nothing. So now what we can do is to do a kind of binary search for the image. We locate the image and then we reconstruct simply by, because we can reconstruct the coefficient and then we can iteratively, reconstruct the first point, then the second point, and so on. It's something simple, but nobody had thought about it. This can be parallelized because at the moment we have been talking all about one neuron, but you can attack in parallel all the neurons. And these are the results. So this is the state of the art. That is this kind of like randomly throwing hyperplane to detect image. And you see that you're ready for 1,000 batch size. It's able to reconstruct less than 10% of the image. And instead, our curve is almost flat, so we can reconstruct everyone. Okay, just to give you an example of what you can reconstruct. So these are the images that we can reconstruct on this batch of 1,000, and this is what the other people could reconstruct. And here we have been very nice because if you take 10 random images, there is no image that they can reconstruct. So we went to look for one image that they could reconstruct, and we put here. Okay. Okay, and that's the end. And happy to take questions.
Okay, thank you, Giovanni. Questions?
Thanks for your talk. It was very inspiring. And I actually have a couple of questions. The first one is about at the beginning of your talk, you mentioned about some timing. Regarding some timing. So we put some examples of time for computation, also for transmission. I would like to know if this is some assumption, if it's an assumption that the computation time can be an order of magnitude lower than the transmission time, because I think that maybe if you consider different volume sizes of data and also maybe different model sizes, this proportion is not. Yeah, and the second question is about the last part of your talk about privacy. If you consider using differential privacy.
Yes. Okay. So the first question, the number I put were number from papers that were studying federated learning on devices. Now, obviously, so the computation time depends on how much data you want to process, but here the idea was to compute just one gradient, no? So if you compute one gradient, so essentially the time is limited by what you can load in parallel in the memory of whatever you use to compute the gradient. Okay? And instead the transmission time depends on the size of the model. So what had happened since that numbers that are very old is that in general we had an improvement of the hardware to compute to do this process on the smartphone, because now many smartphones come with AI specific hardware, so the computation time has been reduced. While on the communication time we don't have the same so much the same improvement. And when you think about a bigger model, well, the communication time scales exactly proportional to the bigger model. So I think the problem, if anything, has been exacerbated in the last years. So the answer, but to go exactly to how you formatted your answer, your question was, well, it was not an hypothesis, it was some measurement, and I think this measurement nowadays probably 6 years. Nowadays is even worse. For the second question about the differential privacy, so yes, it's a solution. For those who don't know, the idea of differential privacy is that before transmitting whatever you want, you add some noise, and this noise some way protects your data. And the nice part of differential privacy is that there are a bunch of mathematical properties. You can compose differential privacy mechanisms and so on. I think there were a lot of hopes for differential privacy, but they are now, I think people do not think now that differential privacy can be the single solution to this kind of problem. Because what you get is that if you try to, on big models, or let's say on models that have high dimensionality, if you compute what is the noise that you need to add to get significant, meaningful differential privacy guarantees, this noise is so big that in practice your model, the quality of your model drops. So overall, the utility privacy trade-off of differential privacy, at least what you get from the theory, is not so convenient. So when you see differential privacy has been used, for example, for the census in USA, very successful. But at the same time, in the census in USA, you may want to protect vectors of dimension, I don't know, 100, or it's not that you want to protect, vectors with millions of parameters, hundreds of millions of parameters. So this affects the.
Yeah.
Okay.
Question?
This is a broader question, and thanks for the presentation. What do you feel are the main bottlenecks for a more mainstream adoption and trust in federated learning? Is it the security and privacy issues, or are the theoretical guarantees that we have or we don't have?
Yeah. No, in terms of both you see, when I say it took 2 years for example, to prove convergence, I mean, during these 2 years, Google was using federated averaging without caring about the convergence or not. So I don't think the main barriers are on the theoretical understanding of the convergence and so on. I think there is indeed, for example, we talk a lot with hospitals and with companies about learning. At the moment, there is for sure a strong issue related to privacy and trusting the other people, that is blocking a wider adoption of federated learning. And also, in some sense, in federated learning, you have also to be in a particular cases where every participant has not enough data to train the model by itself. So it's and the data of the other people is okay. You have more data that is not too far from mine, no? Because for example, if the data of the other is totally different from yours, perhaps you don't in any case want to mix with their data, no? So there is a bit, you know, you need to find case studies where these things are true, and then you need to convince the people to trust. And all these attacks, for example, the understanding how dangerous are these attacks. I mean, the first attacks that were done were kind of like toy attack, no? But you know, so companies are a bit scared to really open their data and not knowing what's going to happen.
Yeah, I was just a curiosity because you were showing lots of ways to attack, but do you also have research on how to prevent these attacks?
Yeah. So it's tricky to. First, the attacks I presented are a bit are both in the family of active attacks, where in some sense there is the attacker is fundamentally the server that is sending you something weird to let you leak more knowledge. Okay. So it's a relatively powerful attacker. There are techniques to protect from this kind of attack. For example, there are techniques based on crypto. So there are techniques where the client can encrypt its update. Every client encrypts, and then the server can average and get the correct result without looking at what is inside the crypto. So these are homeomorphic computing techniques. Okay? So these are nice, I mean, but they are expensive in terms of computation, and also they open the door to other problems because, okay, now the privacy of the user is defended because the server doesn't know what was inside your update. But what if you are trying to attack the server? What if you are the bad guy? And now, obviously, these techniques help the bad guy to hide because I may detect perhaps that someone is attacking me, but I cannot no more expect the update to try to understand who is attacking me.
Mm-hmm.
So you know, it's a tough game.
Complicated, yeah.
I have two questions. First, thank you for the presentation. At the end, you presented that linear layers followed by
Yes.
leak privacy. But indeed, the networks that we use usually are not made up just by linear.
Yeah.
So the performance results that you have obtained are from the, less convolutional layer before you have linear and window layers, or what kind of things could you retrieve?
Yes, there are two things that you can do. First, you can let the previous part of the network mimic an identity. So, for example, some people have proposed, look, I have a convolutional layer. What I can do is let the convolutional layer act essentially as just an identity mapping. That obviously would be very easy to spot, no? Okay, so that's one answer, but there is also another answer. You may think that this kind of attack is not the final attack. In the sense that this attack allows you to reconstruct what arrives to the radio layer. Once you reconstruct what arrives to the radio layer, then, for example, you can apply an optimization-based attack on what is left. And because you don't attack end-to-end, you don't apply end-to-end, now this attack can be more effective than was before. So, but yes, definitely at the moment there are assumptions on the architecture to be able to apply these.
So you can use it as a bootstrap.
Yeah, exactly. You simplify. See, before you had to invert the whole network in some sense, and now you need to invert a piece. And the earlier is this ReLU layer, the easier is the task.
The second question is related to the amount of data each client must have to federated learning. Do you think that increasing the amount of data each client is a good way to improve the security of the privacy of federated learning? Because we actually have a problem, at least with image data, which is usually mislabeled, so you need to label them, and then the amount of data is very reduced. Does it make privacy issues worse? Do you think so?
Yes. In general, on less points you work, the more the update. You see, because in some sense is the sensitivity of the update to the image that you have. So now, if you have less image, the update is really sensitive to this image, so it's easier to attack. So if you have bigger data set, in general, all the attacks are more in trouble. But there are again, for example, you can conceive attacks that allow you to detect more the image with a given label. So for example, okay, you have a lot of data, but perhaps you have only a few data with that label. So I can adapt my attack in such a way that is designed to detect to reconstruct the image with that label, no? And then you can imagine a bit like onion peeling. No, those images are reconstructed in this way. Those images are so.
Do you think that using generative AI we could avoid this kind of attack? So instead of giving my samples to train locally, I generate some synthetic samples to train.
Yeah. Well, some people have been proposing it. Then you are a bit moving the problem because when you create this generative, this synthetic data generator, the risk is that they vomit the data whichever time. So the risk is that yes, you transmit a generator, but then this generator leaks the information. There are people working on it, but I'm not sure if it's if it really solves the problem or not. I know very little about synthetic data generator in any case, so maybe.
Very good. More questions? Okay. So let's thank Giovanni again. Thank you very much.